on linear algebra and its application, sponsored by DBT Star College Scheme. So our today's speaker is Dr. Gaurav Sharma sir from Government PG College, Una. So sir will be talking about linear transformations. So I welcome Dr. Gaurav Sharma sir to please start the presentation.
Interact with the students. So many students have joined this program from different area of our country, different states of our country. So we are really glad to interact with all these students. As all of you know, uh, all these source persons have already mentioned that we have taken this. We are inspired with the lectures from linear algebra geometric approach by S. Kumar Sen sir. And I have also consulted one more book that is very good book, Elementary Linear Algebra with Application by Howard Denton and Chris Rose. So both these books are very helpful for students also. So first I would like to mention the statement given by Satya sir on a very first day of our program, and it was very motivating for all of us. He gave a catching line to our program that think geometrically and prove algebraically. So before starting the definition of formal definition of linear transformation, I will try to visualize linear transformation. We will think it geometrically first, and then we will start defining the linear transformation formally. So if I talk about linear transformation, so the first thing that comes up to mind is this word transformation. So transformation is nothing but it is a mapping or a function. So it can be written as a mapping. Sorry for my bad handwriting. You will have to deal with this in next coming lectures. So if you are not able to understand, then you can ask by unmuting your mic. So transformation can also be taken as a mapping or a function. So the question arises why we have used this word transformation, especially in linear algebra. So let us observe. First, we have already discussed by our source persons, Dr. Sunil and Dr. Rohit, about vector spaces, bases, dependence and linearity. So we have already discussed vector spaces, and the elements in these vector spaces are like vectors. They are like vectors, or we can take them because we are dealing in on real numbers. We are taking R as a field, so we can view them as a point on a vector space. If we talk about R square, on space and so on. So accordingly, the higher dimensions. So we are actually dealing with points. So if we talk about transformation, then we need two sets. So here we are taking vector spaces. So one is V and let other be W. So we are dealing with two vector spaces, and there will be a mapping from V to W. So some points will be mapped to some other vector space. So some point of a one vector space will be mapped to some point of other vector spaces. So if I take particularly to understand what we are doing, if I take V equals to R square, and W is also R square. Then I am we are taking the maps of points on a plane to a points on another plane, right? uh, so a point on a plane means we can view it any point on a plane, that is V, and it can be transformed to some other point. Let us suppose it comes here in W. So if you observe that this point which was here on V, and it is moved to some other point, so it is transformed to some other points. So here it is just a movement of some points from here and there, one vector space to another vector space. So that is why we are particularly taking this word transformation, so rather than mapping or function. So however, we can also use these words mapping and function. There's no problem with that. So let us view this. If we take V as an R square, and I am taking this square grid here, because we want to see what happens to these points if the points lie on this line in these square grids. Then what will happen to them when if I transform this vector space under some any transformation? Not talking about linear, but I'm taking any transformation. So what will happen? Now see, if I suppose now to understand this, we can take an example of rubber sheet, right? So if I take an example of rubber sheet, so we can easily understand what actually a transformation means. So in a vector space, now see, if I consider a rubber sheet as a plane, a point on a plane, right? So if I stretch that rubber sheet, then a stretched rubber sheet will be RW, and that stretching is called transformation, because the point will change. There will be some point here, and after stretching it can move to somewhere else. So that stretching is a transformation, and that new rubber sheet, that deformed rubber sheet, will be our second vector space, that is W. So we can understand with the help of this rubber sheet, example of rubber sheet, that what we mean about the transformation on R square. So suppose rather than stretching that rubber sheet, if I rotate it with some angle, so I will be V will be transformed like this. If I rotate a rubber sheet, then the points here which are in square bed will remain in square bed, but they will rotate through an angle of some angle of 40. Here it is 45-degree angle, because x-axis is this line, which is rotated to an angle of 45 degrees. So this is our new vector space W, right? So this is one example of transformation. So let us observe some other examples of transformation. Suppose if I crush that rubber sheet in any way, then that square grids can be converted into map 2, this W. And in another some way, if I crush it in another some way, then it can be transformed into this map 3. So it can be considered as map 3. So there are many more ways. If I suppose I twist that rubber sheet, then it will be converted like this. V is R square, and W is, now it is a third dimensional space, because I have rotated it, and it has some inclination with z-axis also. So it can be a subset of R cube. And this is another type of transformation in which a square grids are converted into curvy lines, right? So these are few examples of any transformations. So in this way we can understand what is transformation in vector space. But we are particularly talking about linear transformation. So whenever there is a linear word, that something comes to our mind. So my question is, can you guess which of the above transformation? It is just a blind guess. So we have not defined anything about the linear transformation. So there is no rule. There is no. So uh, right now we can only guess which can be a linear and which cannot be a linear. If you want to make a blind guess, then what will then according to you, which one of these following maps can be linear? So if I start from first map, this is our map 1. This is our original V, right? This is our original V. Then we apply map, and then first map is this, W equals to R square. Map 1, map 2, map 3, map 4, and map 5. Now you can guess. Now if anybody want to guess, then he can write yes or yes in chat box. Just a blind guess, nothing. If you say wrong, then it will not matter really, because it is just I have not defined anything yet, so it is just a blind guess, like a lottery. Anybody? So if sir, if you can call any student.
Kavita. Yes, Kavita.
Yes, sir.
Yes, Kavita.
So map 1.
Map 1. Okay.
Yes, sir.
So anybody else want to, you can unmute your mic, and you can have a chat, please. Yes, Shivani Gupta.
Yes, sir.
Yes, Shivani.
Sir, map 1 is a linear.
Okay, map 1 is linear. You think map 1 is linear, right?
Okay.
Okay, you, and you're saying others are not seem they do not seem like they are not linear. Now, can you give any logic or reason why it looks like a linear? The map 1. Chalo, I focus on map 1 because maximum students are saying that it is map 1.
Sir, sir,
Yes,
sir, line are parallels.
line are parallels. Okay. So, okay, but x and y axes are intersecting. There are so many lines which are intersecting. Okay. So it seems, so your guess is actually, yes, Mukul.
So Jyoti is saying that she don't think so that map 1 is a linear transformation.
Okay.
No,
Jyoti, you
sir.
can,
There is
yes.
one
No,
rule
no,
for
no.
map
Actually,
1.
I have one more comment here. Like that origin is preserved there.
Hmm.
That means origin is as it is there. But in other figures, if we think, then origin will change. Like you will change the inclination. This is the same, right? Origin is just here.
Hmm.
But if you can show the second map, yeah, like you are crushing this one.
Hmm.
So these lines will move from here and there.
Okay.
Yes, sir.
So your idea is about origin.
Yes, sir.
So if I fix, suppose here is the origin and here is also origin. Origin is not changed. Then what can you say? Suppose origin is preserved here in map 5. Then what would you say? Is that linear?
I think the word linear says that power should be one.
Okay.
Yes,
Yes.
sir.
So see, we have one idea that the resulting map should also be like it should also be linear. The linear transformation means that that's something related to map to the images of vectors v, vectors of v. So if we say if we see this map, so here the lines, the points on the lines are mapped to the points on the lines. So here the linearity is preserved. So then we can have a guess that this map can be a linear transformation. So first thing that comes to our mind, just like first student said, that lines are parallel. So actually, I think when he saw these mapping, he was considering that lines are mapped into lines, right? So that was the idea. So whenever we talk about some linearity, so first thing that comes to our mind is line. When a line is mapped to lines, into line. So then we say that a map can be a linear. So if we talk about a vector in, suppose let x be a vector in V. So linear combination means if we have a one vector, then what will be the linear combination of this vector? Yes, can anybody guess? What will be the linear combination of this? Linear transformation T. Now, can you imagine these operations? So these are the linear transformation. What we can say, a line is mapped to a line. So whenever the some transformation preserve these two operations, what first one is scalar multiplication. Scalar multiplication. And second is it is a combination of two vectors, two operations. What one is scalar multiplication and other is addition, right? So here along with scalar multiplication, we have a vector addition. Vector addition. So whenever a linear transformation preserves these two operations, first one is scalar multiplication and second one is vector addition, then we say that that transformation is linear. Linear transformation. Yes. अगर आपको, if you understood this concept, why we are taking these preservations, a scalar multiplication and vector addition, then please write yes. Otherwise, I will discuss it again, or we will define formally what is linear transformation. If you have some intuitive idea after discussing this, then we can move further. Please write yes, or if you have any doubt, then you can write no. Okay, so let us define the linear transformation.
Sir, Samriti is saying for repetition.
Okay, so here what I said, whenever we say a linearity, then it gives an idea, it gives us an idea that line is mapped into a line. Whenever a line will be mapped into a line, that transformation will be linear, right? So whenever we talk about linear, so if we take one vector, then its linearity will be alpha x. So line will be alpha x. So if alpha x is mapped into some alpha v, where v belongs to w, then we can say that this t is linear. So line is mapped. So this is our main idea. Line is mapped into a line. So यहाँ पे हमने, we have taken here a linearity of x, and again we are getting a linearity of tx, where tx is the element of w, right? So again, if we take two elements, then its linearity is alpha x plus beta y. So again, Jyoti gave an example that we should preserve the linearity by taking power 1. So we have taken the power 1 only, alpha x plus beta y. So again, we are getting a vectors, linear combination of vectors of w. Tx will be a vector of w, ty will be a vector of w, because these are images of x and y under t, and t is a map from v to w. So whatever we are taking from v, the t will map that point to a vector of w. So here, what am I trying to say, that whenever we say a linear map, so alpha x is transformed to alpha time tx, and if we take two vectors, then its linear combination alpha x plus beta y will be transformed to some alpha tx plus beta ty. So here, if we observe these two transformations, then we see that in first there is a preserve t preserves a scalar multiplication. Scalar multiplication, preserve of scalar multiplication means here there is alpha time x, and here there is alpha time tx, right? So image of alpha x is just alpha times image of x. So here it is a preserve, there is a preserve of addition in which alpha x plus beta y is mapped into alpha tx plus beta ty. So if I want to define a linear transformation, then now we have an idea that two operation is preserved. First one is t of x plus y will mapped to tx plus ty, and second is t of alpha x will be mapped to alpha times tx. So this is the concept of linear transformation. Let v and w be two vector spaces over field f. Then a transformation t, which is defined from v to w, is said to be linear transformation if and only if t of x plus y equals to tx plus ty. So this is the first condition, and second condition is t of alpha x equals to alpha times tx. So if any transformation hold these two conditions, for a vector space V, then we say that this transformation is linear. So there are two conditions for T to be linear. So if we combine these two transformations, if we combine above two conditions, then we get T of alpha x plus beta y equals to alpha times tx plus beta times ty for all x comma y belongs to V, alpha comma beta belongs to F. So F is a field. Now, if up to here, if you understood the concept, then please write yes. Otherwise, we will discuss again. If you have clear why we have defined this linear transformation in this way, then please write yes. And if you have any doubt, then you can ask.
Samriti has asked a question previously. So I
Yes.
think Samriti, if you are hearing me, then are you clear about this concept now?
Yes, sir.
Okay. Sir, you want her to repeat this definition, or should we continue?
Okay, Smriti, are you clear about your doubt?
Yes, sir.
Okay. So here up to this point, we have one conclusion that T preserves two operations. Now, Samriti, can you tell which are these two operations?
Sir, scalar multiplication and addition of vectors.
Yes. Scalar multiplication of vector and vector addition. So these are the two operations that is preserved under this transformation, under linear transformation T. So let us move to the next definition. Now, if V be a vector space over field F, then a function T or a transformation T defined from V to V is said to be linear operator if, again, same condition, T of alpha x plus beta y equals to alpha time tx plus beta time ty. So it is just if we take V to V, a transformation from V to V. So previously we are defining a transformation from V to another vector space W. So if we define a transformation from V to V, then we call it operator. So if transformation is linear, then it is a linear operator. So it is just that we have changed the W with V. So if we define T from V to V, then it is called linear operator, if it satisfies this condition. And next definition is linear functional. So again here, we are replacing W by F, where F is a field. So if we define a function from V to F, vector to field F, then we say that this linear transformation as a linear functional. So again, if it satisfies this condition, that T of alpha x plus beta y equals to alpha time tx plus beta time ty. So let us prove one example so that So this is our vector alpha 1 x plus alpha 2 y. Now I will take the linear transformation of this vector. So here E of alpha 1 x plus alpha 2 y equals to T of this alpha 1 x 1 alpha 2 x2 alpha 1 y1 alpha 2 y2 alpha 1 z1 plus alpha 2 z2. So what will be the resulting image of this transformation? Yes, anybody else? So please ask any student. So our transformation is defined like this: x y z equals to x minus y comma x plus z. So in first place there is a subtraction of first two coordinates, and in second place there is a addition of first and third. So can you guess? Yes.
Yes, Shashi Bala. Shashi Bala.
Yes, sir. Yes, sir.
Yes, beta. What will be the result?
So
Alpha.
alpha 1 x1 plus
Yes.
alpha 2 x2
Yes.
minus alpha 1 by 1
Hmm.
minus alpha 2 by 2 comma
Okay.
alpha 1 x1
Hmm.
alpha 2 x2 plus alpha 1 z1 plus alpha 2 z2.
Very good. So this is our resulting value. So now I will combine the 1 1 and 2 2 separate. Alpha 1 x1. You can mute your mic, Shashi. Alpha 1 x1 minus alpha 1 y1 plus alpha 2 x2 minus alpha 2 y2 comma alpha 1 x1 plus alpha 1 z1 alpha 2 x2 plus alpha 2 z2. Now what would be the next step? I want to separate this alpha 1 and alpha 2.
Avantika. Avantika, MA60.
Keep
Isha.
this
YC Negi. Akanksha Thakur.
Yes, sir.
Yes, Akanksha. Keep this thing in mind that we want to separate all alpha 1 and all alpha 2.
So alpha 1 x1 minus alpha 1 y1
Alpha 1 x1 minus alpha 1 y1
comma x1 plus alpha 1 z1.
Okay, very good.
Then bracket close
Okay,
plus bracket start alpha 2 x2 minus alpha 2 y2 comma alpha 2 x2 plus alpha 2 z2.
right. So next step.
So bracket start
Hmm.
alpha 1 will be common out of these.
Whole bracket, no? If I
Yes,
take
sir.
alpha 1 outside the bracket, then I will get x1
Minus y1 x1 plus z1.
hmm. Taking
Then
alpha.
alpha 2 will be common x2 minus y2 comma x2 plus z2.
Okay. So now this is by the as we have defined t of x, y, z as x minus y comma x plus z. So it is alpha 1 of t of x1, y1, z1 plus alpha 2 of t of x2, y2, z2, or you can write it as t alpha 1 t times x plus alpha 2 t times y. So that means this transformation is linear because it satisfies the given condition. So therefore P is linear transformation. Yes, if you have any doubt, then you can ask. If it is clear, then please write yes. We have taken one example. We proved this the given condition that t of alpha 1x plus alpha 2y equals to alpha 1 times tx plus alpha 2 times ty. So 20 responses are there, but there are almost 45 students are present. So please write quickly if you understood this concept.
Sir,
And I
give them one question, sir. Tx is equal to x and tx is equal to x square, and ask them to think 1 minute, and then ask them which is a linear transformation and which is not.
so
If
for
we
that
take t of
example,
x is equal
okay, t of x equals to
t of x is equal to x, and second one is t of x is equal to x square.
okay. So you can think on these transformations. There is simple transformation from R to R. Both are a transformation defined from R to R.
Gaurav sir.
Yes, sir.
Gaurav sir.
Yes, sir. Yes, sir.
Write one example also. Tx is equal to x plus 1.
Okay.
Tx is equal to x plus 1. They also think that it is a linear transformation or not.
So we can check by this way whether they are preserving these two operations or not. Later we will discuss some properties in which we can check if these are not linear transformations. So for proving that these are not linear transformation, we will check those properties only. So that will make our concept more easy.
Sir, even you have defined the transformation that the line should be mapped into a line.
Yes, yes, yes. Sir, I have given
They
one
can
idea.
use
Yes.
yes.
On
They
this
can
map,
use that.
yes, on this map we can use that concept. A line is mapped to a line. You can see whether here a line is mapped to a line or not. So it is like y equals to x square. It forms a parabola. So you can easily check this is not a linear. This may not be a linear, right? So this is an identity
Sir, I
map.
want to add one more.
Yes, yes, please, sir.
Can we say that a line passing through a region should be mapped into a line passing through a region? Then only the transformation is a linear transformation. Because in the third one, the line is mapped into a line, but it's not passing through the origin, the second one, third one.
Yes, yes, sir.
So line passing through origin should be mapped into a line passing through origin. Then we say the transformation is linear transformation.
That was our intuitive idea. The line is mapped to a line
Yes,
was an
yes.
intuitive idea only.
Yes,
So
that idea gave us that definition.
They gave us the definition, yes. But actually what is happening, we will discuss in properties. We will discuss few properties of linear transformation. That will that will clear more idea about linear transformation. What is
Yes, sir. Yes,
what
definitely.
we have? Yes, what we have defined is how we can check that a transformation is actually a linear transformation with easy ideas. So, should I move forward, sir?
Yes, sir. Yes.
Okay. So our next.
Oh, sir, one Mohammed Farooq. Mohammed, can you unmute your audio? Mohammed. Mohammed Farooq. No, sir.
Okay, Mohammed, you asked that third example is linear transformation or not. You can think on it. We will I will discuss the properties and you will give the answer. I'm sure that you will give correct answer.
Yes,
Let us
Jyoti.
move.
What's your question?
Yes, Jyoti.
Actually, in the first case, t of x equal to x,
Yes.
then this will be at that point only. That means this is obvious that this should be transformation. Like we are taking an element in a plane, so then that will be on that plane only.
Yes, yes.
Yes, sir. So this is an obvious case here.
Yes, it is an identity map. So V is vector into V is mapped into V itself. So there is no change.
Yes, sir.
Yes. Can we move forward now?
Yes, 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 sir.
So there are few important properties that I want to discuss. The first one is, so let us start with, let if T is defined from V to W is a linear transformation. Then first property is T of 0V equals to 0W. That is, a zero vector of V is always mapped to a zero vector of W. Very important property. 0 is always mapped to 0. That was the case Rohit sir was discussing about the third example, that zero line passing through 0 must be mapped to a line passing through 0, because there is 1.0 on that line and that should be mapped to 0 only. And second property is T of minus x equals to minus tx. So additive inverse is mapped to the additive inverse of tx of image also. And additive inverse of x is mapped to additive inverse of its image. And the third property is T of x minus y is equal to T of x minus T of y. So these properties are very easy to prove. So let us prove these properties. So if I take 0v, I have already taken 0v as a vector, 0 of v, 0w as a 0 of vector space w, plus 0v, I will get 0v.
Sir, can they know about this? What is 0v plus 0v equal to 0?
Yes.
Yes, we have discussed very related to this property.
Yes, students, please reply.
You can write in the chat box also. Sir, you can continue.
Okay. So 0v, if I take a map both sides, then I will get T of 0v plus 0v equals to T of 0v. So y. So I'm applying here T of 0v. So can you tell me what will be the image of zero vector to which this element belong, whether it belongs to V or it belongs to W, T of 0V. Yes, I am asking T of 0V will belong to V or W? Yes, it belongs to W vector, right? So that if I want to, so now W is a vector space and this is any element of W. So I can write any vector of W as W plus 0 vector W, right? I can write this. Can I write this? W plus 0 vector W equals to W. So therefore I'm writing of this as plus 0 of W vector, a W vector space. So now by left cancellation, we can apply left cancellation in vector space. So by left cancellation of two vectors, I will get T of 0V equals to 0W.
Sir, keep back. Yes, keep background same.
Okay, so if I if I apply left cancellation, by left cancellation, I'll get T of 0 vector V equals to 0W. So 0 will be mapped to 0 only. Right? I hope this idea is clear. If you are clear about this idea,
Gaurav
then
sir, yes, give them 30 seconds to think.
okay.
The students think on for this property. At least you take 30 seconds, think on it. Then we will discuss another property.
So the proof
If
is
you
very
understand this property, you can write. Yeah.
yeah. The proof is not very difficult. Proof is very simple, but the importantly, so property is very important. So and which states that 0 vector will always be mapped to 0 vector under some linear transformation T. It is very important property. So let us move to second example. Sorry, second property. That is T of minus x equals to minus Tx. So as we know, if we add every vector in V has its additive inverse, and if we add a vector with its additive inverse, then what will we get? We'll get a
Yes, anyone? Yes, anyone?
0 vector. Yes.
0 vector. Yes.
Okay. We'll get a 0 vector, and that 0 vector will belong to V. Right? So that this holds for all x belongs to vector space V. So if I take transformation both sides, x plus minus x equals to T of 0V. So I have already proved that T of 0V is 0 vector of W. And using the linearity of two vectors, I'll get T of x plus T of minus x, because T preserves vector addition. So I'll get T of 0 vector is 0W. Now if I add, because again V is a vector, W is also a vector space, and T of x is a element of W. So it will also contain the additive inverse of this element. Let us add additive inverse both sides. Then we will get t of minus x equals to 0 times minus of tx. So I have added additive inverse both sides. So again, 0 vector of w plus its element is again that element minus of tx. So t of minus x equals to minus of tx. That holds for all x belongs to v. So we have used some simple properties to prove the given result, the given property. So again, the result is very simple. You just observe this result. Result is very simple, but important is very sorry. The property is very important.
Yes, students, if you understand this point, I think sir has written fourth step directly. If you understand this point, then you can write yes. Otherwise, if you have any doubt, so you can unmute the audio. We will discuss.
Yes, I have missed one step intentionally.
If yes, sir, all of right that they.
Okay. So let us move to the third property. Again, third property is again very simple. So
Sir, try to discuss each step with the student.
okay.
I think this property you have discussed first and second property.
Then
So
they can
right,
drive the third one. Yes, they can drive the third one. Now, if we if sir, please call any student.
yes, Aman Shukla. Aman Shukla.
Yes, sir.
Yes, Aman.
Hello.
Yes, Aman.
Yes, sir. Here we can take
T of x minus y.
t of x plus minus y in bracket. Yes,
Very
then
good.
bracket close equals to. Sir, by the definition of linear transformation, we can write it like tx plus t minus y.
Very good.
Yes, sir. And then tx plus by the second definition, we can write it like minus ty.
Yes. So therefore, T of x minus y equals to T of x minus T of y. Right?
Yes, sir. Yes, sir.
So here we have discussed three properties. So first one is 0 vector will map to 0 vector. The additive inverse of a vector in V will be the additive inverse of image of Tx. And third is T of x minus y equals to Tx minus Ty. So we have discussed three examples. The first one was T of x equals to x, T of x equals to x square, T of x equals to x plus 1. So now, Umar, can you see here the 0 vector of R is 0. 0 vector of this R is also 0. So can you now tell us whether this is a linear map or not and why? Why, Umar? Why it is not a linear transform?
You can write the reason also.
You can write the reason also. Why it is not a linear transformation?
Other student also think why this is not a linear transformation. We will call any one of you. You can think how this is not a linear transformation.
Yes, Muhammad. Yes, it will not map to 0. Very right. As I already told you, after discussing these properties, you will himself will tell the reason. So that is why these properties are very important. If we want to prove that some T is not a linear transformation, then these properties are helpful. So it make our life easy. So let us discuss few examples. The first example is r square to r cube be defined by t of x y equals to x plus 1 2y x plus y. So proof, you need to prove that t is not a linear transformation. So what idea you have to prove that this is not a linear transformation? This is the same
Sir,
example.
Sir, give them time. You can
Yes.
take one minute, you think on it, and then we will discuss.
So I'm talking about first example,
Yes,
and
yes.
also you can also think about second example. So we have two examples. Please reply on chat box. 2x minus 3y. It's 2x minus 3y. Again, sorry for bad handwriting. It is 2x minus 3y, x plus 1, 2y, x plus y, and it is 2x minus 3y.
Gaurav sir, can I call one student?
Yes, sir, please.
So, Avantika, Amandeep Kaur, Anita Rana, Bhavna Saini.
Yes, sir.
Yes, Bhavna. What
सर
is the idea about? Yes.
फर्स्ट में जीरो वेक्टर नहीं है.
जीरो वेक्टर नहीं है मतलब?
जब हम x, y को 0,0 पुट करेंगे.
So 0 is not mapped to 0, right?
Yes, sir.
So if I put t of 0, then I will get 1, 0, 0, which is not equal to 0. 0 of r cube.
Yes,
so therefore, t is not linear
transformation.
So you want to discuss the second one also, or we should call to other student? Do you have any idea of
Jashneet.
second?
Let's call Jashneet sir.
Okay.
Jashneet Kaur. Kavita, CS 201.
Yes, sir.
Yes, beta. Do you have an idea about the second example? Second part? How can we prove that this is not a linear transformation? using the property. Terms of what?
मतलब ये एक एक पॉइंट को मतलब वन वन जैसा हर एक पॉइंट अलग अलग पॉइंट को
वो जरूरी नहीं है, वो आपको नेक्स्ट जो मैं डेफिनेशन करूंगा उससे क्लियर हो जाएगा.
ओके सर, थैंक
इट
यू
मे नॉट बी इट मे नॉट बी ऑन टू.
हाँ सर, मैं ऐसे सोच रहे थे कि मतलब 2x माइनस 3y है ना सर, हम 3,2 पॉइंट ले लेते, वो भी तो 0 को मैप होता है ना सर, मतलब 2 पॉइंट 0 को मैप हो रहा है, इसलिए कुछ कॉन्ट्रडिक्शन होता है क्या, ऐसे सोच रहा था मैं.
नहीं, उसमें वो कंडीशन नहीं लगेगी. अभी जैसे डेफिनेशन अगली करेंगे आपको और क्लियर हो जाएगा.
सर कैन आई गौरव सर, कैन आई डिस्कस विद पवन?
यस सर, श्योर.
Yes, Pavan, what is one function?
One function, T of x equal to T of y, then x equal to y.
Okay. Then T of x equal to T of y, then x equal to y.
Yes, sir.
Okay, then how you can define onto?
1 2 for every y there is SD of x equal to y.
Okay, and how you can define bijective?
1 1 1 2, sir. It have
1 1 1 on 2.
yes, sir.
Okay, so I think in next slides,
Yes,
Gaurav shall discuss about bijection map. 1
okay,
1
sir.
on
Okay,
2. Yes. So the inverse of a function, if you know about how the inverse of a function exists, the function should be bijective.
yes, sir.
So you
For
are
the
talking
inverse.
about, yeah, you are talking about that if t of 3 2 is equal to is also equal to
0
0, and
yes,
t of 0 0 is also equal to 0. It means
0
in later lectures we will discuss that there is no bijection if the function is there is no inverse exists if the function is not bijective.
yes, sir.
Yes.
Yes, sir.
Yes, Gaurav sir,
So
you can
yes,
continue.
yes, sir. Here we can have an idea of about 1 1 and on 2. So this map is the first map is 1 1. Here is extra point, but one point is mapped to 1 point, and in second, uh, this is mapping to 1 point only. So 2 points are mapped to 1 point. There is no extra point here. So if this is V, this is W. Then this map is 1 1 and this map is on 2. This is the just a rough idea about what is on 2.
सर ऑल्सो राइट इन 1 1 के नीचे साथ में एंड लिख दे नॉट ऑन टू 1 1 एंड नॉट ऑन टू
1 1 and not on.
ऊपर नॉट ऑन टू और सेकंड में ऑन टू
On
बट
2,
नॉट 1 1.
but not. And let us take another example, which is 1 1 as well as on 2. So this is 1 1 as well as on 2. So but if we talk about linear transformation, I will not discuss about the isomorphism of linear transformation. That is another topic that we will not discuss. But I want to discuss some important transformation, that is zero transformation. Here you can have idea that it is not always 1 1, because if zero transformation is defined as if V and W are two vector spaces, then transformation T from V to W defined by T of x equals to 0 vector for all x belongs to V. So all the points are mapping to 1 point only. So T of x equals to 0. So is called a zero transformation. So this transformation is called zero transformation, in which all the elements are mapped to 1 point only. So now if W contains more than one element, then obviously it will not be an on-to map. And since all the points are mapping to 1 point, so it is not 1 1. So it is not either 1 1 and nor on-to, right? So it is a good example of, now from this example you can see this is the linear map should, then there is no condition that it should be 1 1 as well as on-to.
दो करेगी
Right. So next is identity operator. Again, VF is a vector space, then mapping T from V to V. We have used operator word because it is mapped from V to V, defined by T of x equals to x. That it was discussed also by Rohit sir. We have taken an example from R to R, T of x equals to x. So here it is any vector space V. So T of x equals to x for all x belongs to V is called linear operator. If we prove that if we check whether these are linear transformation or not, so these both the transformation are linear transformation. Zero transformation as well as identity operator are both are linear transformation. So you can do this by yourself. It is not a difficult task for you. Okay, if you have any doubt, then you can ask. Otherwise, I will move to the last slide. It's already 6:13.
So can we define projection as linear transformation?
Sorry, can we define
Projection as linear transformation.
projection? So
Yes, sir.
projection, we need to check whether it is satisfying the property or not. It is just simple. You can check also.
That means it not always be satisfying the linear transformation.
So we need to check then whether.
Shivani, sir, I think some of the students may not be aware of what is projection. Shivani, can you define projection first?
So projection of we can say that projection of some point in different axes. We draw the perpendicular in that plane or on axis to draw the projection.
In a vector space.
Shivani, we will discuss if this after the poll because we are not discussing about projection till now. So maybe other students don't know how we can define projection. So Rohit sir also discussed that there are so many students that they don't know how we define projection. So I think if you
check, Shivani, you can check whether it satisfies the linearity property or not. You can easily check. But by just defining the projection, you can easily check whether it's satisfying the property or not. So it is not a big
yes,
right?
Sir,
Yes.
so in the definition, so why you have written is called linear operator, identity operator.
Yes, because it is defined from V to V itself. So whenever a vector space is defined, any transformation is defined from V to itself, then we use word operator. Which operate within itself, within the vector space.
When the domain and codomain are same, then the transformation, then instead of transformation, we say it's operator.
Yes,
and
sir.
Just to give a distinct, distinct name to this. Whenever we
if
define.
V and W are distinct, yeah, if V and W are distinct, then it's a transformation. If V domain and codomain are same, then we say it's a operator. And if the codomain is a real number or a function, field, then it's a function. Yeah, it's a function.
It's a functional. Just to give another name to make it different from the linear transformation, so we are changing something. I hope there is no other idea. Like differential operator, integral operator, in which we define from one vector space to another same vector space. So we call it operators. So let us move to next definition. If V and W are two vector spaces, we denote the set of all linear transformation from V to W by LVW. And we define the sum of two transformation as S plus T of X equals to Sx plus Tx and alpha times S of X equals to alpha times Sx. So with these operation, LVW forms a vector space. We can check all the properties of vector space, whether they satisfy or not. So we have a zero transformation, so there is a zero vector also. And addition and scalar multiplication is defined, and we can prove the other properties also. So, sir, I hope I have two more important results. So, should I discuss this or we should stop here?
We first launch the poll then we will discuss the result of the
Okay, we can
problem. I
discuss
think
it tomorrow. I will discuss it tomorrow, sir.
yes,
I'll
yes.
stop it. Please, if you can, you launch the poll.
So we will not take more than 5 minutes, and after discussing the poll, you will be free to go. So tomorrow we will meet at 4:30, and you will be advised to join by 4:20. Gaurav sir, is it a wallpaper behind you, or
No, sir, it is not a wallpaper. It is just a picture that Google has included this new, feature.
that's very good? I just saw. I felt that earlier it was not there.
Yes, yes. You can put any anything
My
behind.
observation is correct.
Even I really surprised the books with such as Symmetry and all books are new.
These are all
Thought
linear
you are.
algebra books.
I thought you are sitting in the library.
Yes, yes, yes.
Sir, one question I think Mohammed want to ask. Mohammed, I think your mic is already working now. You can ask.
Sir, I'm asking a question in chat box.
Yes, yes.
Sir, he has written a question in chat box. Let me check. He has written that mod of 2x minus 3y is not equal to 2x minus mod of 2x minus mod of 3y. So is this right?
No, sir, because we have defined the map from R square to R, so it doesn't make any sense.
It is less than equal to.
No, sir.
If it is less.
We cannot separate these two elements just to prove that
Yes,
it is
yes.
not linear transformation because it is defined from R square to R. So,
Okay. Yes, yes. Very good.
Thank you.